All right. Quick reminders. Your programming test is this Saturday. I'll see you there. And it's already confirmed. Just want to just mention one more time. 1006, the prison lab. And your quiz number 3, I also mentioned about the coverage. You can definitely get prepared. And also, in your project specification, it says the team.txt file should be submitted. I already saw several teams submitting theirs. Thank you so much. But if you haven't, do it. Maybe people who are here already, maybe you submitted already. But anyway, I'm going to send an announcement just to remind. And for your milestone number 1, I'm going to maybe either to announce either tomorrow or maybe on Monday about a list of time during the week that your team can actually meet up with me. So I'm going to make it maybe as many times as possible. And then it's going to be a first come, first serve. I'm going to say maybe on Wednesday at midnight, you guys can start signing up for the slot, right? Something like that. Anyway, I'll reach out to you about this. Do you guys got any question already for project? Anything you want me to clarify in the beginning before I go back to Composite? All right, if your team hasn't met to get started, you definitely want to. Right? Things will definitely get busier and busier. Not just this course, but also other courses as well. You definitely don't want to fall behind. OK, and let's now continue with our composite design pattern. Okay, so basically last time we introduced what the problem is. The problem is you want to design recursive system. You got base components, you also got recursive components. And that's basically the nature of abstract syntax tree for Antler 4 when you develop your project, and also assignment number 2, which I'll release on Monday. It's very important. And we talk about 2 design attempts. You should really know why they wouldn't work so well. Maybe they will compile, but they're just not as nice. They definitely got their shortcomings. You should definitely know what they are. And for the 3rd design attempt, it's getting very close. Especially, we created this extra class over here, which is generic over here. And I'm going to show you the final outcome once we get to the actual pattern. Very quick reminder. The reason that we wanted to create this generic parameter is because the composite itself may not be applicable just to equipments in the same projects. It might be applicable to maybe furniture and to any other object type in general. So definitely don't want to say every time I want to create a composite type, I just duplicate this class, which I did last time to show to you. That's something you want to avoid. It actually avoids a design principle called single choice principle, which I will also give you the definition about today. And we're going to use it when we judge the visitor pattern. Okay, so today the plan will be we want to finish composite and hopefully finish visitor pattern as well. And next week we'll go back to parsing. All right, so this is the separate class we want to support so that other packages in the same project may use that as well. Okay. However, what we said in the end of the Tuesday's class, this design is not even going to compile because you actually got one single class over here trying to extend 2 classes over here. It doesn't matter if they're abstract or not. You just cannot do it. Okay. It is some limitation about multiple inheritance being restricted in Java. Okay? So that's something I want to spend a little bit of time about it because it's something very important about design. Okay, multiple inheritance is not supported in general in Java. However, from their official documentation, which I'm going to show to you, you can read it in detail. They claim that they support multiple inheritance in a very restricted way, which I'll show to you. It's not supported in general. Okay, let me go to the slide and show you a little bit of idea. Okay? When I say general, I really meant you want to have maybe certain classes to be the parent class of the same class. All right? Let's now go over some slides, and I'll show you the documentation. Okay, does not support multiple inheritance in general. And if you go to this site over here, and it's from Oracle Java, about multiple inheritance. Basically, when you read about the second paragraph over here, I'll let you read it. It talks about rather than extending from multiple classes, it's not allowed in Java. You can try to implement multiple interfaces in Java. That's what they claim as the multiple inheritance they support. But let's understand this. Can anybody tell me back to your 2030 or maybe 2011. What's really the main difference between abstract class and interface in Java? Yes? Yes, abstract class, you can definitely have the notion of either abstract versus non-abstract methods. In the case of non-abstract method, you can have implementation. True. Anything else? Yeah, exactly. So now, but that's something we just said. You cannot do it in Java for sure. You cannot extend from multiple classes. But now the question is, what's the difference between abstract class and interface? What we just heard is definitely one difference. In abstract class, you can have non-abstract method versus abstract method. It's kind of up to your discretion. Anything else? Yeah, for sure. In the case of interface, you can implement more than one interfaces, for sure. Okay, anything else? What about attributes? William, maybe that's something you're about to say?
I think abstract classes can attribute, but interfaces cannot.
You cannot. I believe in the case of interface, you guys can try it out. In interface, you cannot have the non-static attributes like in normal classes, but you can have static variables. But that's something technical. But let me summarize very quickly. That's important before we dive into the final design for the composite. Okay? Let's start with the abstract class. Let's summarize what you guys should know. For abstract class in Java, number one, you may decide for method. Either it's abstract, using the keyword, or non-abstract, just like a normal method. In which case, it will be inherited to the subclass, and then you can override it if you wish. Right? That's number one. Number two, you can have non-static attributes, or just like a field. Okay? Meaning that the attribute will be a local copy for each object of that particular class. I'm pretty sure you guys learned about it before. And interface, in some way, it's also like an abstract class, except that it is a very special abstract class where every method is abstract. So you don't even bother to mention the abstract keyword in the interface. That's one way to understand it. Okay. You can think about all the methods are abstract, no implementation. And you cannot declare any non-static attributes, but you may try static variables, more like a global one. But you may declare static variables, because if you guys actually want to extend the composite pattern that we talk about in the class, maybe you want to extend some variables to the interface. Static will be your choice if you want to. Okay, just to keep that in mind. All right, one more thing. For abstract class, a class can extend at most one class. And that class either abstract or not, doesn't matter. For example, if your class already extends from one abstract class, can you extend from another non-abstract class? No, you cannot, at most one. Okay? And in the case of the interface, you may implement multiple interfaces. And the interesting interleaving we're going to see for the actual composite pattern, which I'll show very soon, it turns out we might have one class that is going to, number one, extend from an abstract class. At the same time, it will implement another interface. That's kind of the multiple inheritance we'll try in the composite in Java. Okay? All right, just keep that in mind, and then make sure you understand the detail. All right, so let's now go back here. Oh, one more thing, just for your knowledge. Do you guys know why you shouldn't extend from multiple classes in Java? Okay, at the top, let's say. That's awesome. Oh,
Your final thought. If a job doesn't allow you, other languages that have multiple inheritance require you to explicitly specify either a new quotation
yep.
or to call back to, like you need to choose one explicitly.
You gotta somehow resolve the name clashes somehow. Very good. Henry is basically reading my mind. So it's actually here. Okay, multiple inheritance, that's nice. So guys, for your knowledge, you should really know why Java as a language wouldn't actually support multiple inheritance. If they can, if they actually provide a mechanism to resolve the so-called diamond problem. Okay, I'm gonna explain to you a little bit about diamond problem, which Henry just said. Okay, but I'm gonna repeat in a more visual way. Let's assume that multiple inheritance was supported. Then what kind of issue are we gonna run into? Let's say we have a class called S over here, just for superclass, okay? And let's say we got some abstract method over here just called do something, okay? And we're going to create, first of all, at the second level, let's say 2 classes over here. Let's say we got A here, and we got B here. And in order for A and B not to be abstract, we have to implement every abstract method that's inherited, right? That's a rule. So I'm going to implement one version of the do something here. I'll say do something. And also do something. You can think about this is more like a version 1. This is more like a version 2 conceptually. All right? So far we are fine. But what if, since we said assume multiple inheritance would be supported. Let's say we got a class C over here. By having multiple inheritance over here, okay, let's say we don't override anything. Let's have the following code. If I say S, maybe objects would be new C. Right? And you guys should really know why this will compile, because C is a descendant class of S. So this will be static type. That's dynamic type, right? That's what you learned in 2030, so I'm not going to bother you. I assume you know, all right? And what's going to happen now if I say obj dot do something? This is where the problem is. Like what Henry said, there will be some ambiguity. Because now you can see when I say obj dot do something, dynamic type is actually C. According to dynamic binding, we should call the version that's defined in C. But we got 2 versions inherited to here. Unless we have a way to resolve this name clash. Otherwise, it's going to be confusion. So that's why it's not supported. And you, except for Robbie and maybe Chauvin and you as well, if you took an earlier version of 3311 software design course, there is a design language called IFO. Okay? They do support multiple inheritance. The reason that they could support it is because they have a way to say, I can rename, for example, do something into do something 1. Rename do something to do something 2. So when you try to call this method here, you cannot say do something anymore. You got to say do something 1 or do something 2. So there's a way to resolve the name clashes. Okay, just for your information. Right, it's a very important concept over here. Number 1, what multiple inheritance really is. Number 2, why Java wouldn't support it. Number 3, if you want to work around it, you need to have a mix of abstract class, maybe, and also interface. Right? So these are the main points. And diamond problem, that's something you also should know. Okay. All right, so we're going to see the workaround. Okay, now let's go to the ultimate design. But before this, we actually consider 3 attempts, right? That's the final one. And let me just show you, zoom in a little bit so you can see. We have a client over here who declare just equipment objects, which is referring to some interface equipments. And in the interface, we just have a method here called price. And we call this price over here is satisfying something called uniform access. I'll give you some intuition, and then we'll see that in the code. Uniform access. In the following sense, we ultimately want to know, given some, oh, I know what you mean over here. Here, you got equipments over here on the left, and also here you got interface, and you got a price. And the price here is going to satisfy the so-called uniform access principle. What does it mean? given arbitrary equipment, we would like to figure out the price of it. If you're only given some base equipment, the price is easy. Maybe you simply implement as an attributes. On the other hand, if you want to figure out the price of cabinets, for example, it's going to be the aggregation or summation of the prices of all the containing equipments. So that's going to be defined a little bit differently. But from the user, the client's point of view, all they do is to say something like equipment's E, dot price. Depending on what the dynamic type is for E, it could be base, it could be recursive. It depends. Dynamic binding is going to do the trick. Right? That's what I meant by uniform access, which is a nice design principle to satisfy. All right, so that's the interface here, and under which you can see we got, let me talk about, we got some base equipment. So this class over here is kind of optional, but when you see the example code, which I already posted, you can put whatever common source code you want to share, want to be shared between all the base equipment, you can put them there. But if you don't want any common code to be shared, you can get rid of it. It's optional. Okay, I'll put it here. So this one here is optional. It's the share code among the base equipments. There we go. Okay, and you can see here we also got composite equipments: cabinet, chassis, and bus. And let's now take a look at this intermediate abstract class more closely. And here we got multiple inheritance, which compiles because this composite equipment class here implements the interface. At the same time, it extends another class, generic, called composite. So this multiple inheritance is valid. Let's dive a little bit deeper. So remember this generic class over here. We got children, and the type of children is simply just E. You can think about just for this class alone. We got E here, we got E here, and also we got E here. As far as this class is concerned, we are not committing to what the composite type is. So depending on which package you would like to use, you can instantiate the E differently. You will see some diagram just show multiple instantiation a little bit later. Okay? And let's say for this class over here, you can think about this as instantiating the generic type E by equipments. And you can also see that substitution over here. And that's exactly what you have to write. Let me show you right away, okay? And just make sure you're okay with it. Let me go to Eclipse and show to you. If you go under example composite pattern, and then under the patterns package, right, you will see there is one abstract class, composite, right? You can see that's only E. On the other hand, if you go under equipments, if you see under composite equipments, you can see that one there. That's the interesting bit, right? This part here. Let's take a look. The class is called composite equipments. It's not generic because we already instantiate the generic E by passing equipments as the type. You can see we say extends composite, and then where the E is replaced by equipments. That's something you can do. And also implements the equipments interface. Are we okay so far? Okay, that's what you got to do. And you can also read the rest. All right. So that's about the hierarchy over here. The most important class for you to really understand would be this part over here. That will be the one. All right, composite design pattern. And I also included some source code over here. Obviously, that's kind of the problem for attempt number one. If you try to say some base equipments.add, this will not be allowed also. Because you can see the card is actually under the equipments directly. It does not share any composite equipment feature. So that's why you cannot call the add feature, add method, I meant. All right, I'll let you guys maybe pause here just for 30 seconds in case you got any question about the diagram. We haven't seen the code just yet. I'll show you the code a little bit, and then we're going to do some tests just to make sure you know how that works at the runtime. Of course, in your projects, you're going to do more or less a much more complicated hierarchy, possibly one, possibly several, and then handle the tree recursively, right? But that's the base stuff you want to understand. Any question here? All right, everybody's okay? I'll take silence as yes, you're fine. Okay. All right, and then a very important question also to check for later, which we already answered. You want to understand why you want to have a separate generic class over here, as opposed to simply have the children and add code just here. That's basically design attempt number 2. All right, I'll put it here, and that's something you want to review by when you study this pattern. Compare with design attempt number 2, which we spoke about last time. All right, and a final architecture diagram to show to you is to see how we can make this class useful. At the moment, only this class for equipments is instantiating it, but we can do another one. Let's take a look at this one here. Okay, so you can think about this. This is the generic class, Composite. This is the equipment package we just went over. I just had another one. And this one here, I want you to take a little bit closer. You can see this one here is, make it smaller. This one here, if you compare these two. Both of them extend from Composite, but they expand that with different instantiation of E. For one case, equipments. The other one is furniture. However, what we achieve over here is we don't really have to duplicate this particular class twice, which we'll see violates the single choice principle because you got duplicates. But now, it's only a single place we actually store this code. You just instantiate the generic parameter accordingly. Right? So that's the instantiations of the composite pattern you want to see. And so that's what I meant. You may want to instantiate the composite pattern not just once, maybe multiple times in your project. That might be something you want to document in your manual to say, okay, my project is really not only that it works, but also satisfy the good design principle. This is definitely one of them. All right? Any question before I move on? All right? Everybody's okay? Okay, so let's see what else. Okay? I think this one here is just to show you a little bit of code. Let's go over each class very quickly. Okay? So the complete detail also in the source code. And then we're going to do a little bit of tracing just to make sure you understand. Okay? Let me now switch back here. That's kind of the inheritance hierarchy here. And let's take a look. Let's start with the interface. Equipments, we can maybe have price, also we can have name, whatever you need. Remember, only method signature. Right? That's equipment. On the other end, we also got this composite generic class, which we got children, we got add, and you can feel free to add more methods there. Maybe remove, maybe add a particular index, and etc. Right? So these two classes are what we start with. Let's see at the intermediate level what we have. We can have another class called base equipments. Okay? For the base equipment, it simply implements the equipments class. And it has nothing to do with the composite, right? Only base. Okay? And what do we have? Well, in this case, I just got some attributes over here, and then I got some constructor, and then just accessor. Very basic. You guys will work out what kind of common methods or attribute you want all the base equipment or base expression to share in your project. You guys will figure that out. Okay? And for this one here, just reusing the constructor. Okay? That one's not exciting. Let's now take a look at the composite equipments. We only look at the design diagram earlier, but let's now look a little bit more deeper into the code. And let me just give you some look ahead. You will see that I got some comments over here about dynamic binding. That's something you heard back in 2013 and 2011. And I'm going to go over the code very quickly, and then I hope somebody can tell me why dynamic binding will be exercised over here. We'll get there. For composite equipments, you will extend, also implements, multiple inheritance. That's our workaround. And also, every equipment has a name, and also constructor, that's easy, and also the name itself, just return the name. The price here is interesting. Remember, I talked about uniform access principle. Let me just make it even more explicit this time. At the equipment level over here, you can see the price method that every equipment should really implement is called uniform access. So now we got two cases. Case number one, you can see the price for the base equipments will simply return the attributes. There's no computation involved. Whatever price you assign each base equipment, like a cart, drive, and etc., that just return it. That's access one. And what about access two? It is over here. In the case of the composite equipments, how do you figure out? Because composite equipment simply got some children. Each child can be themselves also composite. So it's a tree structure you have to traverse recursively. And over here, let's see. You got a result, and also you want to go over the child one by one. And this, by the way, this is the for each loop. If you have seen that before, you can use it. Or you can use the more traditional for loop, with a loop counter. That's fine too. We'll simply go over the children list one by one. And then every time, we're just going to increment the result by child.price. All right? And again, this one here is also making use of the uniform access, meaning that the single access is going to cover recursive and base cases. And can anybody explain to me why dynamic binding can be exercised in this particular method call? Dynamic binding. Do you guys remember what dynamic binding is? Robbie? Because the child, because the dynamic type itself can either be a base or a composite. Yeah, sure. As we'll see some concrete example how to set this up. Okay, the child. Yes. Now, Robbie, I see what you mean. I didn't notice that. The child over here, the context objects. Its dynamic type can be either the base equipments or the composite equipments. Base or composite. If it happens to be base, it will just return price like attributes. If it happens to be composite for the dynamic type of child, in that case, you're going to involve the recursive calculation of this particular loop until you actually reach some base case and terminates. All right? I'm going to give you guys some maybe hand waving a bit using the diagram, but there's something, hopefully it's not too heavy. Right? So that's about the code for every class that's involved in this composite pattern. Are you guys okay? Okay, hopefully not confused, right? Okay. That's about all the classes I just went over. And once we dynamic binding also explained, let's now try to trace this test case very quickly, and then we are done with the composite. So we can move on to visitor. Okay. Here, why don't you guys stare at this code for just 1 minute? Two things I want you to imagine in your mind. Number one, what kind of tree is being built at the runtime? Number two, when I call this method here, cabinet.price, how exactly is it going to calculate? Okay. Okay, give you 30 seconds more, and then we should really go a little bit deeper into this. Okay. All right, let's now take a look. You might be thinking, well, since the only number that are being mentioned here is 200 and 500, just add them up, and then you got 700. True for this example, but I might ask you in a different way in the quiz or the test. You want to make sure you know how to build that particular tree structure. Okay, we'll see. Let's take a look. All right. So this is the test you just read. Okay. I'll try to use a cost stack to show a little bit. I'll try not to stay here for too long. Otherwise, you can easily get bored. But it's not too difficult to trace. Okay, we'll try. And that's the code for base equipments, which we just went through. That's the composite equipments. And if you remember uniform axis, you will see price over here, base case, just return the attributes, and also price over here, which is going to involve some complicated for loop computation. Right? So we got two cases here. And let's now go over the code very quickly. Over here, just declare the attributes. Right? So we got different variables. We got cabinets, we got chassis, we got bus, we got drive, we got cart. Okay? And we're going to create all these objects. Right? So let's assume we have done that. For example, the car over here, you can see, let's try this one. So the car here, it has a car, and the price is 200. Let me fill out the 200. And also for the disk drive, it's 500. And all the other objects are just like that. Okay? You can, for example, let's say for the cabinets, it has a list of children. I'm cheating a little bit here because eventually it's only going to get only one child. That's why I draw that already. But of course, it starts with empty. Okay? And let's see this part over here. That's how you build a tree. That's the easy part. And we're going to see how to calculate recursively after that. All right, let's try that quickly. So for the bus, add card. So that means for the bus over here, it's going to add as a first child just the card. Right, there's a link over here. And then also we got the chassis. Chassis over here, got bus and drive. The chassis is over here. So the first child will be a bus. The second child will be a drive. Right? Almost, we're going bottom up, basically. Okay? And finally, we got the cabinet. And for the cabinets, the first child will just be a chassis. That's the tree. Here, I'm basically give you the code and ask you to visualize. What I can ask you to do instead, give you somehow the visualization here, or the visualization like this, and then you want to write a Java code to build a tree. You should know both ways. Okay? All right, a final thing for us to do is to see how to trace this line of code. This one, cabinet.price. Of course, if you say drive.price, 500. If you say cart.price, 200. If you say, for example, bus.price, not surprisingly, it's only going to contain 200. Right? It's going to be 200 as well. What about cabinets.price? Right? The answer should be 500 plus 200, but we want to see a little bit into how the recursion works. I think that's really important. All right, let's try. So that's what we will do. So let me start with cabinet.price. And cabinet itself is a composite. So we're going to execute the price over here. Okay? So that means we're going to have some result, and we're going to here to do a for loop. Right? The for loop is going to go over all the child for this cabinet. Okay? Oh, by the way, cabinet is here. Okay? Just in case you didn't see that. And how many iterations are we going to have? Just one. Right? Agree? Just one iteration. And then the result somehow should be updated by the child.price. And this will be the child. So that means the cabinet's price should be equal to the price for its first child. All right? Let me just put a stack over here. I'll try to do a little bit. Okay? So we start with cabinet.price. And to really compute it, we have to say cabinets. Let me use a different color. Dot children at index 0. And then that one there, dot price. Agree? Okay? And how do we compute this particular chassis, its price? We have to, well, because we know this cabinet.children at index 0 dynamic type is chassis. Again, it's composite. So we got to call this version again. So this, when we execute this, let me only go up to here. But what's going to happen here? So when we say this, it has 1 and 2 children. So that means if you try to execute this, you're going to have 2 iterations, right? That one's going to involve chassis, the children, and then index 0, which will compute the price for this one here. And then that one dot price. We're going to do this one first before we can go to the next one, right? And how is this one going to be computed? Well, that one there, too bad, it's just another composite. Agree? So let me go a little bit quicker. In order to calculate the price for this one here, we call the price method on this again, which is going to involve the loop again. And that one there is going to compute the first child, which will give us 200. Okay? So eventually, this part over here is going to give us 200. So that one there is only the first child for the chassis. So what we're going to do is just another one here. We're going to compute the second child of chassis. So, and that will be index 1, the price. That one there, we're lucky. It's just the base case, which will give us 500. And by the way, when you call this price here, it's going to call this version, which will give you just the attribute. So that'll be 500. So eventually, you're just going to add up these two numbers, right? And in your project, I don't think you're actually going to maybe to trace your code like this for the complicated tree. But just in case, if you got any bug in your code about recursion, you may just want to start with some very, very simple test case with some very simple tree and try the method you actually you believe has some error and try to see if you can reproduce some tracing here. That might help for debugging. Okay. All right. All right, any question about composite? It's a very quick review or introduction to the pattern. But you have to make sure you understand the different design attempts and also polymorphism, dynamic binding, and also how things work at the runtime, right? Anything is possible in the quiz or in the exam. Any more questions? Well, you haven't got questions so far. Go ahead.
Why is your video card negative token red?
Just whatever it is.
What's a video card?
Hmm?
It says video card.
You know, I just copied that from some earlier slide. May that make sense? Sure. Yeah. Just some string description. That could be wrong. Okay. All right. I presume everybody's okay? All right. Let's now move on to the visitor design pattern, which depends on the composite. And this slide here simply just summarizes also things that we discussed already. So polymorphism, dynamic binding, the uniform access principle, and also whenever you say equipments.price, depending on the dynamic type, you might call different equipments, either base or recursive. All right? All right, visitor. And for the visitor, the main thing would be at the end, when we talk about the double dispatch. That's something, if you haven't learned about visitor before, that's something you definitely should know when you talk about visitor. And we're going to see, how we can think about visitor is assuming that the system you're trying to apply the visitor to is a recursive system. If your system is simply not recursive, there's no point of applying visitor. All right? That's why Antler 4 actually supports visitor, because abstract syntax tree itself is always recursive. And we're going to see some alternative design, and then we're going to learn about several design principles. We're going to see cohesion, single choice, and also open-close principle, right? So these are the different principles you might have learned in 3311. You have taken the course, or something you will learn later. And then we're going to see visitor design pattern. And we're going to see how you can implement and test the visitor design pattern. Okay. And let's assume we already got this composite structure. I'm omitting some detail over here. I simply put composite expression directly. there should be another inheritance relationship over here about inheriting from composite. I'm just omitting it. But when we present a final design for the visitor, you will see everything. But for now, just easier for discussion. Okay? And that's basically something you had to do for the practice test and also for your tutorial, during the reading week. Let's say we want to design some structure or syntax, abstract syntax for the language. Either you got integer constant, 341, 2, or you got just addition. Right? You can think about extension for later as well. That's OK. OK, let's say that's what we have. And just notice that for composite expression, we got either left or right, assuming there's a binary operation. And here is the question, which will be very relevant to your project. Let's say, given the abstract syntax tree, we actually want to support various operations. I'm just giving you some example. It could be pretty printing. You may want to pretty print maybe the tree in prefix notation, postfix notation, or type check. Of course, there might be other operations you could potentially support. Maybe you want to generate C code or generate Python code from your tree. And the question is, if we try a very naive solution, let's see this. So what we have is, we have this composite tree structure, which we just saw, right? We see how it can be traced. And these are the various operations. I'm going to propose just one possible design, which will work for sure, but is it really the ideal design? Let's give it a try. Since we want to support 1, 2, 3, 4, we want to support 4 operations. Okay? Let me just name them so easier for me to write. Operation number 1, operation number 2, operation number 3, operation number 4. Okay? One obvious design would be, why don't I simply declare all these operations at the expression level, unimplemented? That's for interface. So I can declare operation 1, operation 1, operation 2, operation 3, operation 4, unimplemented. So this was, the nice thing about this is syntactically, Java is going to force all the descendant classes of expression, either base or composite, to always implement operation 1, 2, 3, 4. Agree? OK, let me write it down so you can see more explicitly. And for the constant, I'm going to implement operation 1, operation 2, operation 3, operation 4 in one way. For example, if you want to evaluate the constant, just return a value. Evaluation is pretty easy. And you also need to implement at the composite side for addition. You're going to do operation 1, operation 2, operation 3, operation 4. And obviously, for operation 1, which is evaluates, for the composite, it's going to be harder because you have to make sure the left-hand side is evaluated first, combined with the evaluation result for the right-hand side. Agree? It's just more complicated. That's why I use different color between the two. This is one valid design, which means it will work programmatically. But it violates certain design principles, which I'll show you. But do you guys see intuitively what can go wrong, or what may not be so nice for this design? You can think about, for example, I'll give you a little bit hints. What if a new operation is needed? That's one hint, one way to think about. Number 2, what is the very purpose of a class? So these are the 2 hints. Somehow correspond to the 2 design principles I want to talk about. Any thoughts you guys want to share? What about the first one? If I want to add a new operation, maybe I want to generate some assembly code, let's say, operation number 4. In that way, what should I do? to all the classes? Yeah, William. Yeah, you definitely have to, number one, declare operation number 4 here, and then implement it here, implement it here. Here we're talking about a very small inheritance hierarchy. What if the inheritance hierarchy has many classes over there? In which case, you will need to touch many, many places in your system. So whenever a change is needed, there is a design principle called a single choice principle. You may just want to touch as few places as possible. Okay, that's the number one. And I'll go over the principle in definition. And number 2, a class, right? So there is a notion called Superman class. Have you guys heard about that notion before? Superman class. You might just be able to guess what that really means. What does it really mean when I call a class a Superman class? Well, that means you're having a class that is capable of doing everything you want to do. That's what we intend to do, I would say. You can think about the Superman class is really the extreme, opposite to modularity. Whenever we talk about modularity, that simply means you want to have as many modules as you can, which will collaborate with each other in your project. Superman class means you want to have just a single class where you put all the methods, no matter how related they are, in a single class. Programmatically, this will work, this will also work. But from a design point of view, this should not be the case. That will make the design, make the maintainability just so much worse to achieve. All right? That's just a kind of design principle you want to also consider when you do the project. All right? Let's now go over the 2 design principles here. Okay? So this is one design attempt which will violate 2 design principles. Right? Let's now go over them. One is about cohesion. You don't really want to have a Superman class. So here one can argue the evaluate, print, and also type check, yes, they are like an operation to be applied to the tree. That's true. At the same time, are they really similar operation themselves? Not really. The way you do evaluate has a very different nature of if you just want to print or you just want to type check. You shouldn't really put different kind of operation in a single class. Right? That's one way to argue. Right? So cohesion, that's the definition. You should only put relevant features in the class. That's something you guys can judge. If you got, for example, more than a certain number of methods in your class for handling maybe the programming language or the testing language, it's a warning. You may just want to put them into separate classes that has either inheritance or client-supplier relationship between them. Right? That's something you will have to judge. Right? I can only give you just the principle. And single choice principle, which I also mentioned. The intuitive way to understand it would be you don't want to have duplicates. Right? Or whenever you want to make a change, you should just focus on as few places as possible. So the definition goes like this. And we have to review this single choice principle again once we see the visitor pattern. So when a change is needed, and you just want to change either a single place, if possible, or a minimum number of places. Of course, you want to justify why the multiple places you have to change is really the minimum. It's kind of up to your judgment. Right? So that's why I include. That's another possibility. Okay? And if you really violate, very often it's because you got redundancies. Right? You may, for example, one way to get rid of the redundancy is you can factor out all the duplicates into a single helper method and then call the helper method instead. Right? Like we have a generic class called Composite that can be instantiated by multiple packages in the project. Right? Similar idea. Right? A little bit abstract here, but we'll try to apply these principles as much as we can. All right. Are we okay so far about the principle here? All right, so this slide here is just trying to argue why this design over here is not ideal with respect to a single choice principle and also cohesion. Right? All the points have been just discussed. Okay? And of course, maybe more to your interest, If I give you some certain design, let's say in the quiz or in the test, I would say, now consider this particular design for the following purpose. Now, you want to justify if the design is suitable with respect to maybe cohesion or maybe to single choice principle, right? That's something you will need to know how to justify, all right? Okay, one more principle for today before we talk about the visitor. It's called the open-close principle. It sounds a bit contradictory, right? How can something be open and closed? Basically, it means that for the system or for your package, or I mean for the model package, certain parts ought to be open. Certain parts ought to be closed. Being open means they are unstable. They might just be subject to changes. Being closed means they are very stable. Once they are initially developed, you shouldn't really touch them often. Okay, that's open-close principle. Okay, it's kind of up to your judgment about which part of your system should be open and which part should be closed. But we're going to use the visitor pattern to explain. Let's go over definition quickly. So your classes, features, methods should be open for extension and also closed for modification. But just remember, open means that's the part being unstable. That's why they're open. And closed means they're rather stable. They shouldn't be touched often. Okay? And so here, let's see here. We want to talk about, we're getting very close to the visitor pattern. For our expression language, you need a composite. So there are basically two parts we want to consider. Let me show to you. Okay? We got two categories of stuff. One is about the structure, the syntax. You can think about this part here is what's the antler fork can generate for you, the syntactic structure, okay? The structure part. We got another part which is about the operation we like to support for on the tree. Could be evaluate, pretty print, or type check, right? As many as you like, okay? So we got these two. So our system basically contains these two parts. And now if we want to apply open-close principle, we got two possibilities, right? You wouldn't want to keep the entire system open. You wouldn't want to keep the entire system closed either. So either open-close or close-open, basically. Right? If you look at this table here, right, we're going to talk about these two possibilities quickly. Possibility number one would be, we would say the structure part over here should be open. What does it really mean? That means you're quite flexible of adding new language features. That's what it means to be open. And what does it really mean to be closed? That means once you implement the initial list of initial list of operations, you don't really expect new operation to be added. That's what it means to be closed. Okay, so you can see one possibility is open for the structure and closed for the operation. All right. So open here means the syntax of expression subject to changes. And here, when we talk about the operation being closed, so that means the list of supported operations is pretty much fixed once you develop them. Right? So that means you got to have a very clear idea what you want in the beginning. Okay? That's alternative number one. Okay? So here we haven't talked about anything technical just yet. I just want you to know, for the open-close principle, deciding which part should be open, which part should be closed is completely up to you. But you ought to know what's the consequence if you decide one part should be open, the other one should be closed. That's the main point. Okay? And let's now talk about the second possibility, right? The same system here. So we still got structure, we still got operations over here. And what does it really mean? Alternative number two. We kind of flip, right? So now the structure over here is closed, and the operations over here is open. You can kind of guess what that really means, right? Structure being closed means we don't really expect new syntax to be added. Okay? The close over here, no new syntax. On the other hand, for the open here, you can keep adding new operations. And alternative one or alternative two, you can only decide to be one, but not both. And later on, we want to know, in order for your system to be applicable for a visitor, one of the alternatives should be the case. Okay? That's something we'll see. Okay? And I think the next one will be just the final architecture for a visitor pattern. Why don't we take a 2-minute break by taking attendance? And then we'll go to the visitor. Okay. Okay. All right, let's see. View the course online. Yeah, bear with me, it's a bit slow. Settings, attendance, don't require, allowed, and save. Okay, start the class. Okay, you can check in. All right, no issue, right? All right, can I stop here? All right. Don't. All right, thank you. Yeah, let's take maybe until 3:32, about 2 minutes, and then we'll start a visitor. We should be able to at least finish the double dispatch today. And then there might be some minor stuff we got to finish on Tuesday after the quiz, but it should be enough. Okay, 1 minute. Okay, let's now resume. So we want to go over, first of all, before we dive into code, we want to look at the architecture diagram for the visitor. And I would suggest you can simply just go to the lecture site. I already uploaded the diagram. I'll show you which diagram you should really open, okay, if you got your computer with you. Go to lecture 13. You will see visitor architecture. That'll be larger for you to see. But of course, you can zoom in and zoom out. Okay, so that'll be the one. And to really see the best way to understand the visitor, well, actually, we got a very nice small language to see. So that's why it's reasonably okay to manage. But I'll show you the rule. Okay, and of course, you might think this is not exactly the same as what's being generated by the Antler 4. I agree, not exactly the same, but the general idea is still consistent. maybe I'll just highlight at the end. Okay, let's now take a look. Okay, I assume you can find the diagram yourself. Okay, so let's see here. There are two packages we want to focus on. Okay, one would be the structure. Remember we talked about open-close principle before the break. One will be structure, the other one will be operation. Okay, so we got structure will be one package, which is about the syntax of the AST. We got also operation, and you can see in the operation we got a visitor over here. Okay, and then one thing to note, in the structure part, you can see we basically got the same classes. We got expression, we got constant, addition, the same as before. The only difference is we have added at the top interface level a method called accept. That's the standard term to use for the visitor. Okay, so in the structure part, we got some accept method that every class over here should implement, number one. Number two, on the operations package, we got a visitor interface as well. And under the visitor, the number of methods you want to have, which will force all the descending classes to implement, the number of them depends on how many leaves there are in the structure. Okay, I'll be more precise. Okay, let's see. I'll talk about this one a little bit later. Let's take a look at the visitor. Okay, first of all, you can see visitor here. In Java, the naming convention will be we start with visit, and also visit. Visit constant, visit addition, visit subtraction. Not surprisingly, we got constant, addition, and subtraction. You might see some variance sometimes. For example, you can see addition and subtraction, they got some common intermediate superclass called composite expression. In some cases, you might also see visit composite expression. That's fine too. Right? That's also still being consistent. I'll put it here. I'm talking about the minimalistic visitor. Optional. You might have visit composite expression. That's also possible. Okay? And then let's see what the parameter types are for each of the visitor method. Here, if I say visit constant, constant. Visit addition, addition. Visit subtraction, subtraction. Not surprising, right? And then how many descendant or subclasses you want to have under the visitor depends on how many operations you want to have. You got evaluator, you got pretty printer, you got type checker in this case. Let's brainstorm a little bit. What about for your projects? What kind of operation do you want to apply? Anybody? We can brainstorm. Do you want me to do some, what? Type check definitely applies, right? You may want to do some type checking on the input language. What else? What kind of operation can you do on the AST? Right? You guys want to think about it. I don't want to give you too explicit hints. Right? Think about it. Think about in your projects what kind of operation you want to have. Whatever you come up with, they're going to become some visitor descendant class. And then in that particular class for the operation, you want to make sure you support the visit method for every language structure. That's the idea. Okay? So this is just the architecture. We're going to see exactly how to use it. Okay? I'll get to that very soon. And this part over here is just the composite. Right? You can think about this is just the composite. And then you can see here, this is the main method that we have added in order to support the visitor pattern. This is to say, for any expression, either base or recursive, I can say, let's say expression E. Think about what the consequence is if I try to do this. If I declare it, oh, you know what? Let me put it here. The consequence of this is this. If I say expression E, which will be of certain dynamic type, which can be base or recursive. And if I say E.accept, this accept method over here, what I expect to pass over here would be some visitor. right? And how many possibility are the dynamic types over here? Can be here, can be here, can be here. So that means if I'm given a particular expression, I can simply say E.accept always, depending on what I want to do. If I want a pretty print expression E, I can pass a pretty printer. If I want to do type check on E, I will pass a type checker, and etc. Right? That's what I can read, at least from the architecture over here. Of course, we're going to see more concrete example. All right? Do you guys have any questions just about the architecture here? I think it's reasonably complicated, right? But I think that's kind of the minimum example we can use to illustrate, right? And one thing to say before I show you some example code. You can see there's a client-supplier relationship over here because you can see under the expression at the top level, the parameter type is visitor v. So that's how we link between the expression and also the visitor, right? That's how we link it, just remember. So this arrow over here is really important. So these two packages are not really unrelated. Okay. Any question about this before I move on to maybe a little bit concrete code? Okay. Let's now take a quick look. I don't want to do tracing just yet. At least we can see how we can use it. Okay. Let's say we got composite expression we got expression C1 and C2, which will be constant. That's why I call C. Also, we got some visitor. And notice that, right? This will be reviewing what you learned in 2030, right? Visitor over here is the static type of the visitor. And the static type I'm using here happen to be the top level. That means dynamically, I can bind V to either evaluator or pretty printer or type checker, depending on how I set it up. All right? Hopefully you understand what I mean, right? And let's see how we can set it up. So C1 will be a constant, just with value 1. C2 will be constant 2, and also add will just be C1 and C2. Basically, we are trying to reproduce 1 plus 2, some simple example. But it's a tree, of course. And once we have constructed the composite add, you can see new addition. We pass the left subtree and right subtree. They happen to be just leaves themselves directly, which is OK. And then here you can see this evaluator is the dynamic type of the visitor, right? Doesn't need to be evaluator. If you want to do type checking, you can just say new type checker. Okay? So this will be dynamic type. Dynamic type. And the most critical line, which I briefly mentioned, is this line here. Okay, this line. I say add.accept v. What does that mean conceptually? This is the expression I would like to handle. Normally, it should really refer to the root of the expression tree you want to handle. Or it could be that while you're doing the recursive call, it could be the intermediate subtree you have to handle. That's also possible. But normally you start with the root. Okay, let me just make a note over here. The root of AST to start processing. All right, and then after this, and we're going to trace this line very carefully. It's going to trigger some runtime phenomenon called double dispatch. Whenever people talk about visitor pattern, it's about double dispatch. All right, we'll talk about it, at least for today. Okay, I got 8 minutes. I'll try to do a little bit hand waving. At least you have some idea. We might have to do some detailed tracing in the beginning of Tuesday, but let's do as much as possible. After I have said this, right? This line here is going to involve many things. It's going to involve the visitor V, which happen to be an evaluator, going over the tree structure of this context object, which is add. And then once the processing is finished, the visitor itself stores the result of the processing. That's why you see me say evaluated.result. And I have a very important question for you guys. Very important. Okay? I'll pose the question here. You can see I'm doing some anonymous casting, right? I'm pretty sure you know how to do it. Okay? The question is this. Can I write v dot result without the casting? So instead of casting v to evaluator and then dot result, that one works. Can I do v dot result? If you don't believe you can do it, can you tell me from the diagram, how did you figure that you cannot do it? Anybody? Anybody besides William? I'll be happy to point to him, but you want to try? Yeah. Okay, you try first, please. Yeah, that's pretty much it. Very good. And let me just be a little bit more polished on the answer. The complete answer should be, the V over here was declared to be a static type visitor. The static type of V is visitor. And if you look at the visitor, do we have the result method over here? We don't. Result is only a subclass specific method that's defined over here. So that's why we cannot do it. So the visitor pattern only tells you the minimum methods you have to support, like a visit. If you want to add any operation-specific methods, either for the evaluator, for 3D printer, or other things, you have to add those extra methods at this level. You wouldn't add them over here. All right? Okay, let me just finish the answer here, which does not support result. All right, so that's a little bit about how you can use the visitor pattern. Okay, just basically expression.accept some visitor. And this part would be the most important page. I only got about 5 minutes. I'll see what I can do. Right? I'll hand wave a little bit to you guys. Okay, let me just talk. I'll also make this page available. You guys can do a little bit of mental exercise. Double dispatch is a little bit tricky. Okay, what we want to do is like this. We want to say expression dot accept some visitor. The essence of double dispatch goes like this. Add over here is a reference type. That one has a dynamic type. V here is just another reference type, also has a dynamic type. Agree? Every reference type has a dynamic type, every reference variable. The expression has some dynamic type, which could be, for example, constant, or it could be addition. And the visitor over here also has a dynamic type, which could be, for example, evaluator, 3D printer, or type checker. Right? So now, depending on the combination of the dynamic types, we might end up calling different accept or different visit method. That's really the essence for double dispatch. Okay? So what I would like to do now is to help you a little bit as follows. Let's go over the definition quickly, just in 3 minutes. And I'll give you some hints about what kind of exercise you can do, just to think about double dispatch even before I talk about it. So for the expression part, we got constant, which implements expression. And for the accept, the definition is incredibly easy. Okay? The visitor v is the arguments, the parameter. We'll simply say v dot, since we know we are currently in constant. So we simply say visit constant. And the visit constant method, for example, in the visitor pattern, is expecting some constant objects over here. And what we are passing over here is, since now we are in the context of constant, so why don't we just give this the current objects? So this over here is normally the tricky part to get right. Similarly, when we talk about, let's say, addition, which is just the composite expression, We also got accept to increments, but now we say visit addition, corresponding to the addition here. And then we can just pass this, the current objects. The definition for the accept for each expression class is very standard. No, there's no variance, really. Okay, very quickly, let's take a look at the visitor. I got 2 minutes. Visitor here, we got visit constant, visit addition, visit subtraction. Let's take a look at evaluator, just one of the descending classes. We got some result, and we want to create a visitor. That's fine. Let's take a look at this one here, this one. Okay, I'm going to dive deeper into this next time, but take a look at over here. Think about what's happening here. Visit addition is going to somehow visit the parameter addition. We know that the E over here, which is addition, can be arbitrarily complicated. In general, it could be that E is pointing to some plus, and that one there has 2 arbitrarily complicated subtree. Agree? The left and the right. So the idea about over here, what we have is to say, in order to visit this addition, we have to visit the left subtree first, get a result, and then visit the right subtree, get a result, combine them, so we can set the overall visit result for this plus. Okay? That's kind of the idea. And I don't think you really need to understand double dispatch for the Saturday's test, so I think it's okay for us to talk about double dispatch in detail, maybe on Tuesday. And for Saturday, yeah, just make sure you come before 2 p.m. Me and the TA, we will be there about 1:45 in the person lab. We'll set up the room very quickly, and then once we think you're ready, you can come in. All right? Guys, do you have any question? And one more reminder. You ought to submit your team.txt file to the project init folder. If you haven't, please do so. All right, I'll see you guys on Saturday.